If you want to use a computer to solve a problem of any substance, you somehow have to model the problem. Well, what does model mean? Model means that you have to store in the computer, that is, you have to write a program to represent all of the aspects of the problem that are relevant so that you can write an algorithm to solve the problem. This is often called modeling. Modeling means representing all of the characteristics of any problem. So what are the characteristics? Well, at a high level, it is simply the state of the system. That is, what are the things of the system that can change. If you're trying to model a pair of glasses, you might care about whether they're open or closed and what the prescription of the lens is. That's kind of a trivial example. If you want to model the weather, a much more difficult example, then you have to store the state, which is the temperature and the wind and the precipitation and the clouds at every location, right? So you have to start by storing the state or the values of the things that can change. Then you have to think about what external forces can influence the state of the system. That is, what are the inputs to the system that can affect the system? And finally, you want your model to be able to do something. So given the current state and the inputs, you can choose to do something. And that is performing an action, which the action might change the internal state of the system, or it might cause some external output. So in the end, most computer simulations, which is a fancy word for saying any computer application really, because all applications are essentially a simulation of some model, have three things: an input that affects the state, and some action that might affect the state or might produce output. So I've mentioned some things we might model. Weather system, that's a really complicated one. But it turns out, even though that's really complicated, it's really important. And there are a lot of important things that we like to model with computers. The stock market, right? People like to write programs to make money. And so they do that by modeling the stock market. What is the state of the market? What kinds of things are changing externally that are going to influence the market? And then what kind of action should you take to affect the market? In other words, how do you write a computer program to make money in the stock market? How about disease? Suppose we want to model a disease so that we can try and understand how it works and improve it. We have to understand everything about the disease as it is manifested inside the body of the creature that is being diseased. We have to know what kinds of things can input, and we have to have algorithms that model how that disease changes the state of the body and what kind of things it can produce and influence the outside world. All right, those are big important problems that we really care about. We're not going to start by writing programs for the weather, the stock markets, or disease. Let's look at some really simple things that we might model. How about a fly, like this moth on my window screen? Well, what kinds of state does it have? It has a location, right? It is at a place. Maybe it is hungry or not hungry. It might get scared if it senses something that could hurt it, if it's in danger. And it might be tired. Maybe it doesn't feel like flying. Maybe it would rather rest. That's a simple representation of the state of a fly or a moth. That creature can sense some things about the outside world. It can sense danger. They often can sense light. And maybe it can sense some food, so it knows whether it wants to go to find some food and eat it. And finally, it can perform various actions. It might be able to fly, and if it flies, it can decide where it's going to fly. If it's flying, it might decide to land, and if it's going to land, it has to decide where it's going to land. And if it's by food and it's hungry, maybe it can eat. Right? Those are all things that the fly can do. So finally, we want to put all those things together and define an algorithm that can describe how a fly can behave. So let's take a look at how we might represent this algorithm. And there's lots of different ways. I'm going to start by drawing a picture. So this is how we're going to represent the model to start, along with the algorithm. We start by thinking about the state, and we're going to draw state with simple circles. So one of the elements of the state is whether the fly is scared. So we will say that this circle represents that the fly is scared. If the fly is scared and it senses, if it's scared, then what it can do is it can perform the action of flying until it is not scared. If it's not scared and it also is hungry, so maybe we'll represent this by having two circles. It is not scared and it is hungry. Then what if it senses food? Well, if it senses food, perhaps by having a dashed line saying that it senses food at a certain place, then it can perform the action of flying to the food. Well, the act of flying to the food doesn't make it stop being hungry because it hasn't eaten yet. So actually, it's going to fly towards the food, but it's still hungry. Now, if on the other hand, it is at the food, because it has flied so far that it has reached the food, then it can eat the food. So this is at food. Then it can eat, and it now is not hungry. If it's not hungry and it senses light, then it might fly toward the light. The point is, you can define what the fly does through a representation of the states, what it senses, what its actions are, and how those actions affect its state. Finally, let's take the algorithm we just drew as a picture and rewrite it as pseudocode. That is, as text in a way that more closely represents how we're going to write this as a program for a computer. And we're going to do it with a sequence of conditionals. That is, we're going to say if the state of the fly is a certain thing and it senses a certain something else, then this is what it should do. And here's what that algorithm looks like. If the fly is scared, then it should fly randomly. If it's hungry, then it should do something different depending on its state and what it senses. If it senses food, then it should fly to the food. If it's tired and it's flying and there's no food, well, then it should land. On the other hand, if it's already at the food and it's flying, then it should land. If it's at that food and it's not flying, well, then finally it can eat. All right, then if it isn't scared and it's not hungry, then it can look for light. And if it senses light and it's not tired, then it should fly to the light. One of the interesting things about writing pseudocode, which is going to turn into writing code for computers, is that we can represent exactly the same algorithm in very different ways. So here is a structure for exactly the same algorithm, but structured differently. And it does it by nesting if statements and tying things together. So for example, in the middle it says if it's hungry and if it's at food. So if both of those things are true, then it checks to see if it's currently flying, and if so, then it lands, and if it's not flying, then it eats. You can see this is actually a clearer structure by organizing the conditions in a hierarchical manner rather than sequencing them all together. Now we're ready to start looking at code.